Thank you very much. So I would like first to really thank the organizers for giving me an opportunity to speak in front of this expert audience. And I say this because I'm not an expert. And for those who might have heard me talk before, so I would like to say that the novelty in this talk is that now we can do any dimension, and that in order to treat any dimension, we have a sort of new approach that works better and is easier in a way, which I will describe in this talk. And also some novelty will be at the very end with the ongoing work that I will present. Okay, so we're interested in Coulomb gas Hamiltonian, very simple. But now so the interaction is Coulombic in dimension bigger than 3 or in dimension 2, and it can be log in dimension 1, which is not Coulombic. It's a log interaction. Okay, so of course, something like this does not necessarily come from a matrix model, especially if you're dimension bigger than 3. And we will use the fact that W is the Coulomb potential. So it solves, it's a fundamental solution to the Laplacian, except up to a constant factor, which is CD. This constant depending on dimension, just because you don't want to have these constants lying in front here. So this thing will be floating around in the formulas. And we have a confining potential, which is growing at infinity fast enough and smooth enough. Okay, and of course, you can be interested in the states with temperature. The Gibbs measure is this, and you want to understand, in particular, the partition function in the limit of large n. Okay, so I think here I don't need to give, everybody knows motivations for this. So statistical mechanics and the connection to random matrices, which is famous. And many works on such models. Another motivation is also originating in computational complexity. So people who look at Fekete sets, in particular, there is a lot of work around the team of SAF around understanding minimizers of logarithmic energies on manifolds, and in particular on spheres, which can be viewed as limits of Rees and energy interactions of this form. Okay. All right, so let me recall the setup and some notation. So it's well known that for minimizers of the Hamiltonian, you converge. The empirical measure converges to the equilibrium measure, which is the unique minimizer of this continuum energy here, which I will denote E. And the minimum of the energy is behaving like n squared times the minimum of E. Okay, so this works in any dimension without too much difficulty. There is a unique minimizer. It's the Frostman equilibrium measure. And I will denote by sigma the droplet or the support of the equilibrium measure. And for convenience, assume that sigma is nice. So it has a nice boundary. And this is really for technical reasons. But so if dimension is bigger than 2, we also assume that the equilibrium measure has a density bounded above and below on its support, which is regular in the support. This again is for convenience, and if dimension is 1, you can treat the case of the semicircle, whose density obviously doesn't have a uniform bound from below, but it's fine too. Okay, it's also known that if you look at states with temperature, you have an LDP that corresponds to this thing, which is proven. So basically, there is large deviations for the empirical measures at speed n squared, with essentially this E as the rate function. And this was proven by various people according to dimension and stuff. So it's not difficult to have a general LDP valid for any potential and all these dimensions. Okay, so everything that is not converging to the equilibrium measure has exponentially small probability with speed n squared. What we're interested in is looking at next order, the next order behavior. And this will be done by expanding the empirical measure as, well, n times the equilibrium measure plus a remainder. And seeing this, the fluctuation, if you want, as a sort of error term. And inserting into the Hamiltonian to see what comes out at the next order. And the idea is that at the next order, the next order will tell you something about the microscopic behavior of the configurations. Okay. So just for the story, it started as work with Etienne Sandier, where we developed an approach that was essentially two-dimensional, and it was inspired from our previous work on vortices in Ginzburg-Landau, the model of superconductivity. Okay, so it will work for minus log in dimensions 1 and 2, but it fails to work in higher dimensions. So in work with Nicolas Rougerie, we developed an alternative approach, which instead is based on Onsager's lemma, and I will describe. Okay, so in superconductors, you have objects that are called vortices. There are filaments of vorticity around which there is a superconducting current. And the Ginzburg-Landau model is a variational model that tells you, what ground states should behave like. They should minimize a certain energy. And it turns out that when you do an asymptotic analysis using techniques of calculus of variations and PDEs, etc., you find that the vortices really behave like interacting Coulomb particles in 2D. So the true interaction of the vortices behind all this, behind the functional itself, there is a sort of reduced interaction, which is purely points interacting with the log interaction. Yes.
It's not Coulomb in the superconductor, it's Coulomb in the fluid.
Okay, you mean because
the interactions are short phase.
Yeah, it's a Yukawa potential. In reality, it's a minus Laplace u plus u, but when you zoom, when you look at microscopic scale, it becomes essentially like the Coulomb potential. So we worked on this, and then we saw that you develop tools that work for essentially Coulomb interactions, and so then you try to see what happens, and what you can say about just simple models, this simple discrete model of Coulomb particles. But I don't have time to get into the Ginzburg-Landau story, obviously. If you're interested, it's an interesting topic too. Okay. All right. So one of the punchlines of our results is an expansion just on the minimum of the energy. So we just look at the Hamiltonian here and just try to minimize it. There is no temperature. And as I said, you go to next order. So you see the leading order is this n squared times the energy of the equilibrium measure, E of mu naught, as expected. And then what lies beyond, so in dimensions 1 and 2, there is an n log n term, which is fixed. And then what lies beyond is at order n to the 2 minus 2 over d. And in dimension 1 and 2, it's order n. And we identify the constant that lies here. It's related to the equilibrium measure. So you see that this mu0 is the density of the equilibrium measure. So this is the way it depends on the potential. And otherwise, it depends on a constant alpha, which only depends on dimension and not on the potential, and which we identify as the minimum of a certain energy W, which will be the main object of the talk. So there is something that's called W, the renormalized energy, whose minimum governs the next order terms. And the idea is that minimizers for the Hamiltonian are going to want to minimize this thing. Okay, and so at least you have an expansion of the minimal energy, and then I will say at the end, I will give statements on the behavior of minimizers themselves. With our analysis, of course, you can input this understanding of the Hamiltonian at next order. You can input it in the Gibbs measure, and it gives you some expansion of the partition function. So you put the log here of the partition function, and here you put the same expression that I had on the previous slide. which is correct up to little o of n2 minus 2 over d. And you make an error from this, which depends on temperature, and of course, which decreases as temperature goes to 0, whereas beta goes to infinity. So this gives a next order expansion of the partition function, which at least gives you the idea of what the next order is, and it becomes precise when temperature goes to 0. At the very end, I will show you how we are hoping now to get something that's really the asymptotic term in order n to the 2 minus 2 over d. And this is valid for any dimension. As you know, partition functions are well understood and computed in dimension 1. In dimension 2, there is already much less. And I think in dimension 3, beyond the leading order, I don't know anything. OK, so this also tells you that there should be a transition regime which corresponds to beta much bigger than n to the 2 over d minus 1. And beta much bigger than 1 in dimensions 1 and 2. So this is the right scaling if you want to see essentially a crystallization of the system. So maybe that's not completely obvious, but it comes from the scaling. OK, so as I said, the next order term tells you something about the microscopic configuration. So here is the setup. We have sigma, the droplet, which is the support of the equilibrium measure. We have endpoints typically living in there. And so you zoom around a point at the scale n to the 1 over dimension in order to get a configuration that has typical spacing 1. Okay, and then these configurations of points, we call them capital lambda. And as n goes to infinity, of course, they start to fill up the whole space. So you get essentially like a point configuration in whole space. And the idea is that after this blow up, these points should interact according to a Coulomb interaction, but screened by a fixed background charge, and that's called, in physics, a Gelium. I will explain, of course. OK, so the whole thing has to be expressed not in terms of the point themselves, but it's more convenient to express everything in terms of the potential, like an electrostatic potential generated by these points seen as electrostatic charges. Okay, so you view the points xi's as positive charges, and the n mu 0, n times the equilibrium measure, you view it as a negative neutralizing charge, if you want. And you have to zoom everything, as I said. So everything with primes will denote blown up quantities. Okay, so mu 0 prime is the blown up of the equilibrium measure. And xi prime are the blown up of the points. And then you define hn, this potential that lives at the blown up scale, as precisely the inverse Laplacian of this configuration of charges with the constant CD. So it's nothing else than convolving this distribution with the Coulomb potential W. Okay, so it will be quite important in our analysis that when you convolve with this potential W, you find a function Hn, which is a solution of an elliptic equation, right? Laplacian H equals blah. And this equation is local. That's the crucial point, the fact that you're solving for a local operator. Because then it allows you to localize things in space, as opposed to a situation where the operator would be non-local, and so all space would sort of play a role. Okay, so the next step is to perform a smearing out of the charges. So these charges are singular. They're going to create a problem near the diagonal. As we know, actually, I can rewind a little bit for people who missed the first slide. So this is the Hamiltonian we're looking at, right, the Coulomb interaction. And you see here you have to take out, of course, you have to remove the diagonal from the interaction. Corresponds to infinite terms. And these, so these singular charges at the Dirac masses at the points create a divergent energy. And so a way to get rid of this is to smear out the Dirac masses. So we will consider delta x superscript eta to be, for example, the characteristic function of a ball of radius eta normalized by the volume. So this is now this is a nice function with integral 1, positive, and radial. Okay, smeared out Dirac at scale eta. So Newton's theorem tells us something very nice. It tells us that the potentials generated in this way by the Dirac mass and the smeared out Dirac mass, so that means W and W convolved with this, coincide outside of the ball of radius eta. And that's because the smearing out is radial. Okay, and not only they coincide, but there is always an inequality. There is a relation between W and W convolved. That's true pointwise. Okay, so then what you can do is you can look at the smeared out potentials, where you simply replace, so you take the same formula, but you replace the Dirac masses by the smeared out Dirac masses, and you define this as Hn, comma, eta. So it's non-ambiguous, and it coincides with Hn outside of the balls, and of course, as eta goes to 0, you will recover the thing, except that you cut off the singular part of the potential. So instead of behaving like W, like log, or like 1 over x to the d minus 2 near each point, it's sort of is very large, but it's not blowing up.
So are you in 2 or more dimensions now? Or?
Okay, so I'm presenting the whole situation in 2 and more, and I will make a note about dimension 1, which has to be treated a bit differently. But it also works in dimension 1. Okay. So for now, it's 2 and higher.
But these considerations wouldn't work in 1D, right?
No, it wouldn't work in 1D because in 1D, log is not the Coulomb kernel. But you can, there's a little trick that allows you to go from embed 1D into 2D and get back to the 2D situation. So in fact, you can treat 1D as if it was 2D. In fact. And that's not very difficult. Okay, so now we use something which is inspired from Onsager's lemma, a famous thing in the stability of matter. You use that from Newton's theorem. You can bound from below the total, the sum of the total Coulomb interactions by the interactions between the smeared out charges. Okay, so because of Newton's theorem, when you smear out the charges, you just decrease the total repulsion of the guys. And now that you have smooth, smeared out charges, you can reinsert the diagonal if you want. So now I'm making a double sum with all the interactions taken into account, including the self-interactions, which I later remove. So you put back the diagonal and you remove it. It's a fixed term now. Of course, it's translation invariant, so it's just a constant depending on the scale at which you smear out, and it's going to blow up like W of L, obviously, like the potential of L. So when L goes to infinity, this thing blows up. But you subtract it n times for the endpoints. And now this thing is nice because it can be integrated and expressed as a function of the potential, of the smeared out potential. So what you do next is first you split. So the sum of the smeared out charges, you split them as announced as the equilibrium measure times n plus a remainder. You insert that in there. You combine it with a well-known characterization of the equilibrium measure. So you might know this. So if you take W convolved with the equilibrium measure plus 1/2 of the potential, the characterization is that this thing is constant in the droplet, in the support of the equilibrium measure, and it's bigger outside. Right? So there is a picture like this. You have the droplet here. You have a function which is constant and which is bigger. And so you call this whole function, you call it zeta. You make this a definition of zeta. And so zeta is 0 in the support and non-negative outside. And it turns out that the constant, you can compute it, and it's exactly this. So this is known. But this thing is quite convenient because when you insert the splitting, it will make the cross terms essentially cancel out nicely. So the fact that you're expanding around the equilibrium measure, if you want, is causing the first order terms to essentially disappear. It's like a Taylor expansion. So. Okay, and then you choose the smearing out scale appropriately. You want it to be a small constant eta times n to the minus 1 over d, which is the natural scale of interaction. And then you blow up everything by n to the 1 over d, so the smearing out will become eta. And when you insert everything, as I said, and you recombine terms, you get an identity, which is valid. So for any d bigger than 2, any n, any configuration of points, any eta, you have this bound from below. And of course, the bound from below becomes an equality if you let eta go to 0. So the Hamiltonian, with all the terms, including the potential terms, you see that it decouples into the leading order term n squared times E of mu naught. Then there is a term in n log n that comes out from the scaling of dimension 2. And there would be the same term in dimension 1. And then this term here, you see, is the integral of gradients of the potential squared. So you've transformed this sum of pairwise interactions into simply a Dirichlet energy of the potential. And because you have put back the diagonal into the mix, it nicely integrates into this. So just a simple integration by parts. Now what you recover here is these diagonal contributions that had to be subtracted and which will diverge as eta goes to 0. There is a constant kappa d in front, which is completely, just something explicit depending on dimension. Okay, so you see this thing gets factored by n to the 1 minus 2 over d. There is an error in eta square, which will go to 0 as eta goes to 0. And there is an effective potential that comes out, which is the function zeta I was talking about, which just simply now is confining. It's acting like the confining potential, but it's 0 in the droplet. So it's just confining things to lie in the droplet. And you can sort of ignore it because it's non-negative. And so what I claim is that the red term is the interesting thing. And what we're going to do, of course, is to take a limit of this red term as n goes to infinity and eta goes to 0. So we will call this a renormalized energy because you see this thing is a way to take a sort of infinite energy and cut out the divergent part. Okay. So now a note on dimension 1, as I promised. So what you do for dimension 1 is you embed the real line into the plane. And then you use the fact that logarithm is really a two-dimensional interaction. And you can form the potential generated in the plane by your distribution of points. So just view your points as points of coordinates xi prime 0. They all lie on the real axis. And the equilibrium measure, you view it as a singular measure on the real line. Okay, and then everything lives in 2D. And it's, in fact, when you take the gradient of this potential, so the log, it's just the same as taking the Stieltjes transform. There's not really anything surprising. But then you can continue the computations with this. And this whole splitting formula works as well. Yes?
So this is a one-dimensional Coulomb gas, but it's logarithmic interval.
Yeah, so it's not a Coulomb gas, it's a log gas.
Yes.
In one dimension, it's a log gas. And in all other dimensions, it's a Coulomb gas.
Well, of course, there's also a one-dimensional Coulomb gas.
Yes.
That would give some interest.
But that's, yes, so we didn't study this because for the most part, it's well understood. It has been well studied in the 70s and 80s. There is work of Lennart, Eisenman, Martin. So this was not our focus. But yes, you can be interested in a Coulomb gas in 1D. Okay, so now we have this potential. As I recall, it solves something like this, minus Laplacian. I go back to dimension 2 and higher, just for simplicity. So the sum of the Dirac mass at the blown up points minus the blown up equilibrium measure. This is how I define my potential. So of course, when you take the limit as n goes to infinity, you're going to center around a certain point x naught in the droplet. And when you take a limit, you get solutions of an equation of this form. So you're going to get a sum over a discrete set of delta masses, possibly with multiplicities, because maybe some points would converge to the same point. And the background density, the equilibrium measure blown up, is converging to a constant. Because you're zooming a smooth function, it's behaving like a constant. So this is where you make the assumptions of regularity on the equilibrium measure density are playing a role. And the constant, of course, is the value of mu naught at the point where you blow up. So this, I insist, has to be seen as a constant. And corresponding to this, you have the smeared out potential in the limit setting. Same thing with the smeared out charges. And now we have an infinite set of points, right? Because we're taking the limit, so it's filling up the whole space. And next, we're going to define the limiting energy on such a set of points. So given any m is going to correspond to this background density. You see, mu naught of x naught. In fact, what mu naught of x naught is telling you, it's telling you how many points per unit volumes there should be near the point x naught. So now this becomes a constant. And I take all, I call AM the class of all gradient H of solutions of something of this form. And in order to define a meaningful quantity, we take a limit over large boxes of precisely terms of the same form as I studied before. So we're going to define W to be the lim inf as eta goes to 0. In fact, it's a limit. Of the lim sup as R goes to infinity, of the average over larger boxes, of the gradient of the smeared out potential squared, minus, so here you subtract off precisely the divergent part that you expect from the self-interaction cost of each point, which of course gets multiplied by the density of points, by the expected density of points, m. So per unit volume, you're going to have m points, and that's exactly what you subtract off from this thing. Okay, so we've gone from a situation with points in whole space to an interaction energy which is phrased in terms of a potential that's generated by the point. So you can't really completely avoid this potential because there is a non-uniqueness of a solution to such an equation in the whole space. You can add a harmonic function and you will get another potential. Yes?
So do you know whether the potential function has a distributional limit in the scaling limit or only its gradient?
I think only its gradient. Yeah. So we can prove that there exists a limiting process of the gradient. So the gradient of the potential, you can view it as an electric field, right? And there is an electric field process. And you can talk about a limiting electric field process and things. But I think the H itself does not have, it's not tight. Right? So that's why everything really depends on gradient of H. Okay. So this is where we had before an alternate definition with Etienne Sandier, which worked in dimension 1 and 2. And which is the thing we built from Ginzburg-Landau theory. And in a way, it was more complicated, and it corresponded to reversing the order of the limits. So limit when eta goes to 0 and when R goes to infinity were essentially reversed, and that can lead you to a different answer. But it's not very important because at the minimum, it's behaving in the same way. Okay, but I don't want to get into this. So a few remarks. So W being finite will tell you necessarily that your density of points has to be m. So if you fix yourself an m and you compute this thing is going to be finite only if m is the right density of points. And then by scaling, you can always reduce to density 1 because, you scale everything and you see how things transform. And there's going to be a factor for the transformation of the scaling. And this is the factors that we saw actually in the first formula. So you can study everything on A1. And you can prove that W is bounded below and has minimizers over the class. And you can even show that there are sequences of periodic minimizers with larger and larger period. But now the big mystery, in a way, is to identify minimizers of this thing. So you may not like the formula that defines W. So I will show you that at least if you have a configuration of points which has some periodicity, then you can recover a more palatable formula, something that depends only on the points. Okay, so if you have a configuration A1 AM, which is sort of living in a torus and repeated periodically, then W you can compute is going to be a sum of pairwise interactions between the points of G of Aj minus Ak plus an explicit constant. And these are explicit constants. And G now, instead of the Coulomb kernel, it's the Green's function of the torus, of the underlying torus. So it's the Coulomb kernel, but somehow periodized. And it has a singularity which behaves like the Coulomb kernel. And now you have something more explicit, and you recover what you would hope, a sum of pairwise Coulomb interactions. But I want to insist on the fact that it's not just a system of Coulomb charges, it's a system of Coulomb charges with a fixed background, here M, to neutralize. Otherwise, there is no hope that such a thing could converge. So you see, this thing is saying that the energy, the total pairwise interaction energy, is scaling like volume. So it's scaling like number of points instead of scaling like number of points squared. And so it's not the class of things which will satisfy something like that have to be configurations that are relatively well ordered because there are a number of there has to be a sort of charge balance on large boxes. And this is the only hope that this can scale like number of particles instead of number to the square. Okay, so we have only some partial minimization results. So the first result is that if you're in dimension 1 with the log interaction, then you have a W, which I didn't write, but which I explained is computed by embedding into the plane, blah, blah. And for this one, you can identify the minimum. Over the class A1, it's the lattice distribution. It's when you put points exactly periodically, also called sometimes the clock distribution. Again, you have to normalize density of points. So in dimension 1, it's solved. But in dimension 2 and higher even more, then we don't know, and the only thing we can compute is the minimum over perfect lattice configurations with fixed volume. So you take all lattices in dimension 2 that have volume 1 for their fundamental cell, and you find that the triangular lattice, which is this guy, is the optimizer in this class. And in fact, the proof is borrowed from number theory results. It's about the minimization of the Epstein zeta function, sum over points in a lattice of 1 over p to the s. This is known to be minimized at the triangular lattice, and this was proven in the 50s. Within lattices? Yeah, within huh? Near lattice? I don't want to claim anything. I mean, it's possible, but it should be, but I don't have a proof. Okay, so then you can ask yourself what is in higher dimension. So even among lattices in higher dimension, there is no result. There is no corresponding result. In dimension 3, of course, you can think that a good candidate is the FCC face-centered cubic lattice, but the corresponding number theory result is not available even in dimension 3. So even among lattices, we don't know which one should be an optimizer. So at least in dimension 2, you can risk phrasing a conjecture, which is that this triangular lattice maybe is really the global minimizer among all possible configurations. And so we call it Abrikosov because precisely we made this conjecture in the context of vortices in the Ginzburg-Landau model. And as I said, in superconductors you see vortices, but what you see is they align themselves in perfect triangular lattices. So they form exactly these shapes. And since we showed that they should minimize W, and the experiments, on the other hand, show that they form lattices, it becomes plausible that this really is achieving the minimum. Okay, a few other remarks. So a student of Sandier, Betterman, showed that this conjecture is equivalent to a conjecture of Brochard, Hardin, and Saff that they made on the value of the order n term in the expansion of the minimal logarithmic energy on a sphere. So when you take points on a sphere and you compute the sum of log, they had a conjecture on what the order n term should be, and if their conjecture is equivalent to our conjecture. Another remark, of course, is that because of the first theorem I showed you, solving the conjecture or identifying the minimum of W in any dimension, it's equivalent to computing the beta tends to infinity limit of the order n term in the log of the partition function. Okay, so if anybody knows how to compute the log of the partition function, it would solve the conjecture. But okay, so I'm hoping for help here. No, but it's when beta goes to infinity. Yeah. So when beta goes to infinity, you're essentially converging to minimizers. No, I don't understand. I mean, yeah, but okay, but that would not, you would not fill it in the value of W. So,
Is the conjecture that this is a minimizer?
It's a minimizer. Okay, it's a minimizer. You take this guy and you perturb it sometimes. It will still give you the same value, but still this number, the value of this. No, I'm not saying, no, I'm not saying the global minimizer is the one I predict. I'm saying the value of the minimum is the value at the one I predict. It's the energy, right? It's a minimizer. Right?
Do you also, would you take the next step and assume that the unique minimizer up to translations and
No, because the way we compute, at least the way we compute the energy, it doesn't feel a compact perturbation. So you can always perturb it in a compact set, and if you're taking a large thermodynamic limit, it's not going to feel. So if you want to have a uniqueness result, you have to do something. You have to place some boundary conditions or some periodicity conditions. As phrased, the problem is it's not rigid enough to give you uniqueness. It's a question of how you define the function, right?
If you have a cylinder, then you do have a periodic.
Yeah, so this is
like the one-dimensional.
Yeah, this is this statement, right? If you have a torus, then you have.
No, I'm talking about a cylinder. So it's periodic in one direction, infinite in the other direction.
Okay, then maybe you can hope to prove something.
Then you can prove that it's periodic.
Yeah. Yeah, it's Eisenman.
But would it depend on
I mean,
it certainly depends on that.
in all these questions of crystallization, if you want to phrase a crystallization result, you have to have some sort of boundary condition. For example, you say, okay, I freeze the configuration outside the box, and then I let it move in the box, or you put some periodic boundary condition or something, because it's a little too relaxed otherwise. But the conjecture is only saying it's a global minimizer. Okay? So the value of the minimum. Even okay, but maybe we can discuss later because otherwise we're going to get into a long. Okay. So so maybe the last remark is that in any case W we sort of understand it as a way of measuring the disorder of a point configuration. So with something, the most ordered being something periodic, and the higher the W, the more disorder. And you can show that with W you can control things such as fluctuations of number of points, things like that. Okay, so we have a result in dimension 2 with Rota Nodari, which is just on minimizers now. So no temperature with all the assumptions that I said before. And this result is telling you rigidity, if you want, of the number of points. So nu n prime is the density of points at the blown up scale, right? The sum of blown up Diracs. So it's telling you that the number of points in a big box is exactly the number of points of the equilibrium measure up to an error L. So this is in dimension 2. So in dimension 2, you take KL, KL I should have said is a square of size L. And so you take any square of size L, which you look at the zoomed scale, you take a large square, and it tells you that the number of points in the square is exactly what you expect plus an error L, and that's obviously optimal because even for a lattice you cannot do better than that. And it also tells you that you have equidistribution of energy in the sense that if you compute the potential, the smeared out potential generated by the configurations in the box of size L, and you properly renormalize it, then it's equal to the minimum of W integrated with respect to the box again.
Is this essentially Gauss's law?
What is Gauss's law? Sorry.
That you can compute the charge by integrating the flux of the electric field.
This result? Yeah, this result you can view it like that. So this result is a corollary of that in a way. So once you understand how the energy is spreading, how the electric field is you can of course integrate by parts and you retrieve this. Yes. Okay, so this is a result of rigidity. It doesn't go all the way to the boundary. There is a problem at the boundary, and I think this is something not coincidental, but okay. So we did it in dimension 2, but I think there is no problem in extending it to any dimension, and it's to be compared with the result of Hammer and Ortega-Cerda, who obtained by very different techniques. They obtain only the first result, so the distribution of points, but with an error which is less good, and they don't have, of course, they don't have anything about the equidistribution of energy. So this thing should tell you that you should locally always look like a, hopefully, triangular lattice. Okay, so now I want to state results on the situation with temperature, and I recall the setting, right? You have the droplet sigma, and you blow up, etc. So we're going to try to state results in terms of the electric field process, or in terms of the potential process. So what we do is you take the normalized Lebesgue measure on the droplet, and you push forward, and you make a probability measure which is going to keep track of the blow-up point. Right? So X is a blow-up point in the droplet, so you keep a label of the blow-up point. And then in the second entry, you put the gradient of the potential generated near this blow-up point, so blown up near X. So n to the 1 over dx is the zoomed center, and then you look at this. So this makes a collection of things on which you put a probability measure Pn. the push forward. Okay. And Hn is defined as I said before. Okay, so what you can show is that Pn is tight as soon as your next order terms are bounded by the order that I said is the right order, n to the 2 minus 2 over d. So you get a tightness, and so it converges to some probability p, which is going to be weighted on blow-up centers, comma, electric field. So the probability p belongs to the class C. It's a bit, sorry, it's a lot of notation, but which are probabilities such that the first marginal is the normalized Lebesgue measure. That's trivial by construction. P is translation invariant. That's also a easy consequence of its definition. And for P, almost every couple, gradient of H has to be in the class A mu naught of X. Why is that? Because you zoom around X, you remember? So the density of points around a zoom blown up point X should be the equilibrium measure at that point. And so that's what we define as the class A mu naught. X is the class of configuration of points in all space whose average density is the subscript. Right? Okay, and then you can define a W tilde on these P's, which will simply be the integration of W of grad H against the measure P. So if you want, it's like the average of all the renormalized energies of the configurations, the average over all possible blow-up centers. And when you compute this average, you are essentially recovering the whole energy. So it's like you're taking a box, if you want, and you're randomizing your box over the droplet, and you're looking at the energy in each box, and then when you re-average, it's giving you the whole energy. So the W tilde has a minimum over the class C, and you can compute. It's just the minimum of W properly integrated and computed over the corresponding class each time. And since we have a formula for the scaling of how this thing scales in terms of the index here, we recover the formula that was in the first slide. We're going to recover these types of formulas, you see, where alpha now is the minimum of W on the class A1. Okay, so I come back. And so now I can state a result that's more precise. It's telling you something about the configurations now. So you take x1, xn, and you define the Pn as above, the process on their potentials, if you want. Up to extraction, you have conversions to a process in the class C, and you can bound from below the energy at the next order, you see. So you subtract off the leading order, you subtract off the n log n term, and you normalize by the right factor, and now finally you get a bound from below in terms of the W tilde of P. And this is true for any configuration, and what's more, so this is a bit of work, but what's also more work is we want to show that this lower bound is sharp, which means you can achieve equality. And so for minimizers, you're going to have equality with the minimum of this W tilde. And in order to do that, of course, you have to construct by hand a configuration whose Hamiltonian is going to be small enough so that you have the inequality in the reverse side. And it gives you as a corollary that, of course, if you're a minimizer, then your P, your limiting P, has to minimize W tilde over the class C. And so that means informally that if you take a minimizer and you zoom again around almost every point, you should see a configuration of points which minimize W. So conjecturally, a lattice, something of this that looks a bit like a lattice. So this result, of course, is less strong than the result with Rota-Nodari, because with Rota-Nodari, we take minimizers and we show that really around every point, every window that you look, you have the right energy. This thing is telling you something weaker. However, it's true for any configuration, this lower bound. It's valid for all configurations. not necessarily minimizers. And so because you have this lower bound, you can insert it into the Gibbs measure, and then you can say stuff about states with temperature. Right? It allows you to get bounds on the probability of certain events. And so this is what you have in the following theorem. Okay, so it's a sort of LDP style estimate. Okay, so there is this scale n to the 1 minus 2 over d that comes into play. You define beta bar to be the right scale temperature. And when beta bar goes to 0, this constant c is going to go to 0. And this thing is telling you that the probability of an event an, so a configurations of points, right, is decaying with the exponent n to the 2 minus 2 over d. So in dimension 2, it's n, right? It's a speed n thing. And it's decaying like the infimum of W tilde over the limits p's, the p's belonging to the limits of the set an, minus the minimum of W tilde. So sorry, I did not define this constant CD, but it's the minimum of this W tilde over the class C.
Does this give you Gaussian fluctuations?
But it's
Is the right scaling of the variance being proportional to the perimeter of the surface? And that was shown by Martin and Jelsen.
yeah.
It was a case of, I guess, real Coulomb system, but
Yeah.
something valid for the
I don't know how to answer. I don't think it directly gives you that. It's a sort of different nature of statement. So
I think it's true.
I think it might. The problem is that this statement, you see, is becoming sharp only when beta goes to infinity. In any case, if you manage to do it with to do something with every beta, then maybe you have a chance for Gaussian fluctuation.
I think that is really proven.
Yeah, it should be fine.
Finite beta.
Yeah. Okay, so at least for now, the result as stated here is telling you that if W tilde, you see, at the limit is above a certain constant, a certain threshold, then you have exponentially small probability. So it means that everything should have some order, but not the maximal order, right? So as with temperature, there is a certain order, and as temperature decreases, C beta bar is going to go to 0, and so you're going to have more and more order until at beta infinite you should see minimizers. Right? You have a question? Go for it. So this here, this is beta. This is beta, and just this thing is a function of beta bar. If beta is fixed, it's even better because then, okay, in dimension 1 and 2 there is this term, you don't need it. In dimension 3, it's 1 minus 2/3, so it's going to infinity even faster. It's telling you that in dimension 3, you don't even need to go to beta fixed. It's happening even earlier, the crystallization. So this thing we expect is somehow telling you that things should crystallize, computed in this averaged way. Things should crystallize as temperature goes to 0 sufficiently fast or sufficiently slow, according to this measurement. Okay, and so what is the set A infinity? Is the limits of all the PNs that you form from your points. So you see it's the limit of the potential, electric field processes computed, blah, blah, blah. So this is to be compared, if you want, to the LDP that is known at speed n squared, which is just an LDP on the empirical measures. This is more like an LDP type thing on the process at the microscopic scale. on the electric field process at the microscopic frame. And so what we're really hoping to do now, and this is ongoing work with my student Thomas Leblay, is to really get the full LDP. So this is not a full LDP, it's just an upper bound. But we're hoping to get a full LDP at this speed. And the rate function should be beta over 2 times this W tilde plus an entropy term, which is to be computed as a specific relative entropy with respect to a Poisson process. So it's going to measure essentially the entropy of these blown up configurations of points. And of course, what you recover from this, that if beta goes to infinity, it's the term W tilde that matters. And if beta is fixed, then there is a sort of balance between order and disorder. And it's the match of these two that should govern the situation. So if this is true, of course, at least it's going to give the existence of the order n, or n to the 1 minus 2 over d term in the log z expansion, so the existence of a thermodynamic limit. And it also should show that there is crystallization when temperature goes to 0, but not before.
What do you mean by crystallization?
No. Okay, I'm exaggerating here. I mean convergence to minimizers of this guy. If you want to believe that this. Yeah, no, of course, symmetry breaking is still possible. There's a lot of this is very weak to see. It's too weak to see such a detailed structure, but it's just telling you at the level of the energy, you should converge to minimizers of this. But at least in any case, it should not happen before temperature really goes to 0, which I think it's, at least in the physics literature, you often see statements that there should be a critical temperature.
So in which dimension are you now?
Any dimension.
So out to dimension 3, then apparently you have an n to minus 1/3 behavior.
Yes.
So when n goes to infinity, beta can be all very small.
Well, yeah, you have to scale beta with n. It's often the case that in fact beta should be scaled with n in a problem. It's not.
But there may be confusion here. When physicists talk about phase transitions, crystallization, probably they refer to translation symmetry breaking.
That's true. That's true. That's true. Yeah.
Whereas here you mean, I presume, that the distribution of the point process collapses onto this periodic process.
Yeah. Exactly. I agree. It's not exactly the same definition.
So what's the statement in 3 dimensions about crystallization? I'm a little confused. Do I have to, like, if my system size gets big, what happens to beta? How do I read that? Is it n over? I don't know whether d minus 1 is in the denominator or
No. So if, okay, so this is n to the minus 1/3.
Okay.
So if n to the 1/3 times beta goes to infinity, you should already be in the regime where things have frozen. I mean, this is what comes out from the computations. I don't have any explanation for this, but it seems that. Frozen means, in the sense that the rate function is governed only by this W tilde. Well, of course, look, this is ongoing work, so I don't want to completely swear everything, but at least in dimension 2, it's just saying beta goes to infinity, and in dimension 1 also, it's the same.
Match together is the comments that were made. So are you sort of proving that in dimension 3, sort of you have symmetry breaking in this extreme sense, that you're sort of always collapsing to the fully
If your temperature is
well, it fits that.
it's just that the temperature has to be scaled differently with the number of points.
No, but
If you fix temperature, maybe it seems to be that. Okay, I see there is not. I will check this, but I think it says that. Yes. because this statement I am sure, and you see this thing here is 0 in dimension 3 with fixed temperature. So it's telling you this. Okay, so the other thing that we're doing is, in fact, that it turns out that everything I said depended on the fact that the potential was Coulomb, because you use the locality of the operator that's associated. In fact, you can do Riesz kernels, so non-Coulomb kernels, as long as S is between D minus 2 and D. And you can obtain similar results, renormalize energy and SPLA. And the idea is to transform the operator that's associated to this kernel into a local operator by using extension of space dimension. So it's a trick that was popularized by Caffarelli and Silvestre in the study of non-local equations. So you see the kernel 1 over x to the s is the kernel of a fractional Laplacian operator. And if you take your space Rd and you embed it into Rd plus 1, this kernel becomes the kernel of a local operator, which is of the form divergence of y to the a. You're solving equations of the form divergence of y to the a grad u equals delta, where y is the transverse direction, and a is an exponent that depends on s. And so with this trick, you recover the situation of a local operator, and then you can do these the sort of same cuttings and pastings that we were doing before. Of course, there's a bit more work, but we think we can adapt the approach to treat such interaction. Okay, so I thank you for your attention. Have some references.